This is going to be a somewhat of a superficial presentation of randomized algorithms. But I just want you to be aware of this class of algorithms, especially the potential it has with regards to the kind of things that we want to do. Okay? If I had not mentioned this earlier, there are two major strategies for parallelization. So when we sort of think about taking a large problem, this stupid thing. We have a large problem and we want to act on it in a distributed fashion. This used to work so well. I don't know what is going wrong with this guy. Okay, you can ignore this for the time being. So the first, of course, is what we've been doing, which is a divide and conquer. Take it, break it up into chunks, like what we've been doing with RDDs. You have a large array, it's broken up into small pieces, and we operate on each of them, right? So loosely, I'm calling that divide and conquer in the sense that you divide it and operate on each of them in parallel. The other strategy is randomization. Okay. Now, some of you might think that where does randomization come in here? And that sort of, hopefully, I'll answer that towards the end of this lecture in terms of why randomization is a very powerful tool in trying to do things in parallel. If you want a very intuitive thing right up front, is that the reason why we're not able to do several actions in parallel is because of deadlock or contention. I need to read or write this to this location and somebody else wants to do it as well, and so we compete with each other and it becomes difficult. Randomization is a very powerful tool which allows us to break these deadlocks. So if we look at randomizing the way in which data will be processed or accessed, then that leads to an algorithm or a class of algorithms that are easier to parallelize. A general trend that you would see with a lot of randomized algorithms is that they are extremely easy to understand, as you would see in today's lecture. They're very easy to implement, but where the hard part is improving bounds and correctness of these methods. So luckily we're not covering any of those things today. We're only looking at the class of problems where we can do it. So from a parallel perspective, what you're looking at is that you're basically trying to use randomization to make local decisions with which a very high probability, they're not guaranteed, but with a very high probability, add up to good global decisions. And that's what you're trying to do, okay? A good example for those of you who are still somewhat confused about what a randomized algorithm is, I just sort of bring you to this notion of sort of either sampling a data, and you can think in terms of doing quicksort. So quicksort is a classical randomized algorithm. You randomly choose a pivot, and I'm stressing on the word random, and based on this pivot, I divide it into two pieces. So in some sense, it's both a randomized as well as a divide and conquer algorithm, right? You can think in terms of trying to sort in parallel. Maybe we will cover sorting later in the class. So you want to take your numbers, pick a random value which divides into two, and then recurse on that. Again, randomly picking samples which allow you to do this, right? And that's sort of where you win out. What would be a non-randomized version of doing this? Sort of think in terms of quicksort, think in terms of how you would implement it sequentially, and what would be the challenge in trying to do this in parallel, and where randomization comes in. This is a very sort of almost a contrived example, but think about it. So, who wants to come up with a parallel version of quicksort? Okay. Describe, if you were to implement quicksort sequentially, how would you do it?
Take a pivot and take a pivot.
How do you choose the pivot?
Like, if you don't want to stretch, we must just pick first from C.
What? Sorry?
Just like how can you just always take the last element or something? Does it?
First or the last?
Yeah. More or less.
Any other suggestions? So, what is the problem? and again, for those of you, you're probably doing this in your algos class if you're doing it this semester, but how? So we have an array here, right? So A is equal to some array, right? So what do? We can do something like pivot is equal to A of 0. Some people said this, right? Typically, people try to come up with heuristics out here. What would you do? You can take A n by 2, A n minus 1, take the median of these, which is a good choice, okay? So this starts being less randomized in the sense. We are trying to sample our distribution. This is arguably really bad, but you can maybe choose 5 samples or 7 samples or whatever else you think is convenient. What did I do? First element, last element, middle element. Let me choose the median of these 3, right? Because ideally, if I want to parallelize it, if I want to divide it up, I want my partitions to be somewhat equal, right? Otherwise, you're getting very skewed. This is also true for traditional quicksort, where the depth of the recursion, if you remember initially we talked about the work depth model, wherein the depth dictates how long it takes. And so if it's the tree that you create, the recursion tree that you create is not balanced, then you're going to have a problem. And then of course you get your left and right elements, the ones which are less than or equal to and the ones which are greater than the pivot, and you recurse, right? So that is a randomized algorithm for you, and that's sort of a loose parallel version for you as well, okay? The usual technique in a lot of these algorithms is going to rely on some form of sampling. The proofs are going to depend on what sort of distribution you assume and how you are going to sample your data. Like I said, we are missing it. We're not going into too much detail today. A very common thing, at least from the perspective of parallelization, is the use of randomization in symmetry breaking, right? Think of a lot of operations that we're doing. There is symmetry, which means that it is not clear that one or more memory accesses in which order they should be performed. And that ends up being a symmetry, and you want to break the symmetry. Things which have an order defined have a stage in which it should be done, and there are no repercussions to doing it differently. In this particular case, when you have an issue of multiple entities, execution units which could act, which doesn't have a fixed order, then you could end up in a deadlock, okay? And today what we're going to do is, along this line, is basically a very common thing for breaking symmetry, and it's the computation of independent sets. So given a large set, say for example, we're going to look at graphs today. If you have a lot of sets, how can we divide it into independent sets such that there is no contention between them? And that, you can imagine, is the first step towards parallelizing any algorithm. If you can extract independent sets, they can all operate independent of each other. The other issues, of course, of load balancing. An example is quicksort, which means that I want to sample it, get a good estimate of the data distribution so that I can make sure that my division of work is not exactly equal, but is somewhat load balanced, which is also important. When you're doing a project, you'll probably encounter some of these issues. I sort of introduced graphs with the assignment. I'm sort of just revising that again. We are going to go into a lot more detail later. But a graph is basically a set of vertices and edges. So it's a combination. We talked about the equivalence between matrices and graphs. So going from a graph to a matrix to a graph means that the adjacency graph of matrix A, wherein an edge exists if that corresponding matrix entry is not equal to 0. And if there is an edge weight that corresponds to the value of this Aij value in the matrix. Correspondingly, you can do the right opposite and go from a graph to a matrix, where if you have a weighted graph, you get a proper matrix with values. Otherwise, the default weight of 1 represents an edge. We also talked about how symmetric matrices are going to lead to undirected graphs, and unsymmetric or asymmetric matrices are going to lead to directed graphs. Okay, just a very quick review of this. So loosely, these are some of the problems that we're going to consider. One of the hardest problems, especially when you want to do graph problems on a large scale in a distributed fashion, is the problem of partitioning a graph. You want to take a graph and you want to break it up into pieces. If you remember, in all the problems, we've been taking our big problem and breaking it up into smaller chunks so that we can process or do whatever computations we're interested in. Graph partitioning is a very, very hard problem. So this sort of becomes a chicken and egg problem. It's an expensive operation which becomes a prerequisite for doing any other operation on this in parallel if it's large enough. It's NP hard. We will cover this in detail possibly after fall break. And it's an NP hard problem, so most of the approaches that end up being produced are somewhat ad hoc or are approximation algorithms. So you want to be somewhat quick and get a reasonably good graph partitioning, right? One of the associated problems is coloring, which again ends up being chicken and egg, which means that in order to do coloring properly, which is the problem we're going to cover today, you need a good partition, and in order to do a good partition, coloring would be helpful if you had a good coloring. They're also related to the problems of graph Laplacian and eigen problems. So if you remember in PageRank, when we considered a large network and a corresponding matrix, we were estimating the primary eigenvector. Partitioning would be related to the second smallest eigenvector, which will give us the best way to partition a graph. So they're all related to the mathematical concepts, and we'll cover this in much more detail later. Breadth first search and depth first search. Everybody should know what these are. You can think in terms of the complexity of trying to do this in parallel in an efficient fashion. Because when you're, let's say you're doing a depth first search, you could potentially traverse across the entire graph, starting from one process, ending up on another. So it ends up being a very tightly coupled problem. So how do you actually do these kind of things? The other problem which you sort of looked at least thought about in terms of the PageRank case, is that of connected components. How connected are they? Can you reach any page from any other page, or any graph node from any other node? Are they connected? And if they are, can we compute a spanning tree, which is the minimalistic, the tree of, or the graph of edges with the least weight, which are connecting all our values. So these are just some of the algorithms that we will sort of go through later in the which is the focus today. Like I said, this is going to be a pleasant little thing. So graph coloring goes back to early cartographers. So you have a nice map, and what you would like to do, this by the way is an example of a planar graph. You want to color countries so that no two countries which are distinct, which share a border, have the same color. So these two are touching each other, so this is yellow, this is blue, and you don't want, just so that it's easy to represent. I'm sure all of you in your high school or earlier geography lessons, you've sort of seen these kind of maps, right? So this is the key question. Now you can imagine a graph being formed from one of these cases. Now in case of planar graphs, there are theoretical proofs on the number of colors that are required to color it. What we want is that if we have an arbitrary graph, all you're given is some nodes, like the countries out here, and edges, which are effectively saying that these two share a border, or in our perspective, these two have a dependency on data access or communication, right? So we can take any problem and break it down into independent units of execution and their dependencies, which would again be a graph, right? So the question is that how do you actually color a graph? Does it make sense? Does everybody understand the problem? Right? So we'll sort of look at one other issue here. Sorry, I should bring this up, which is sort of the chromaticity of a graph, or the number of colors that I'm going to require to color it up, right? So what would be what sort of bound can you give me for this algorithm? How many colors do I need?
Maximum degree.
Degree plus one. Worst case, right? We'll in general do better, but worst case, I might end up in a situation where I am of degree D, and I have D neighbors, all of which have different colors, which forces me to choose D plus one, right? Simple proof. So it's not terribly bad. We have a bound on this thing. The cost is not, again, terribly bad. It's sort of order the number of edges, right? Because what we're looking at. So reasonable. Let's sort of look. Baby example. We're gonna keep seeing this graph again and again, because I was just too lazy to draw different graphs. How many colors? Take a guess. Louder, come on. The no. 8, 7. 8, 7, 6. 8. Okay. Nobody's going lower than 6. Okay. Let's do this. So I'm going to start somewhere here. I forgot which one I started off with, and I'm kind of going to go counterclockwise. Okay. I'm going to sort of. I think I spiral out like this. That's my order. It doesn't matter. You can choose any order. So that's my first guy. So I'm going to go the internal nodes first, and then I'm going to go outside. So first one I picked red. Okay. These are just the default colors in the order that PowerPoint was suggesting to me. So let's start with this. Let's consider this one. What should I color? This one?
Not red.
Not red. Okay. So everybody answer, because like I said, this is a fun class. So not red. So this is the next color offered. Who?
Orange.
This one. This is my next guy.
Orange. Red.
Red. Because why would I choose a new color if I could reuse my colors, right? So red. This one.
Orange.
Why? New, right? Because there's an edge here, right? So now I'm going to probably go into this one, I think. Okay? Huh? Orange, right? Okay. Next one.
Yellow.
Okay? Next. Red. New, right? Because you now have a case where we have that. Next one.
Purple.
Okay. Now, we only took 4 colors, so it's not as bad as it looks. You can easily, even with a greedy algorithm, come up with something better than this. Okay. Now I want you to focus a little bit on some of these cases. You probably can massage this a little bit. So it's not exactly the best example I can give, but sort of look at this particular scenario out here where, let's say I didn't want to use blue out there, or this whatever bluish shade that I have. If I colored this yellow, I could have used an orange here, right? Without violating any of these. And basically this tells you the complexity that this is a greedy algorithm, so local variations are not going to improve my solution. I'm not looking for these cases. I'm not optimizing it at that level. Because I'm not thinking of what should I color so that the next one is also optimized, or the next one after that, right? But if you think in terms of what we have done, again, arguably this is a very trivial case. It's not so bad, is it? So you were all thinking it's going to take 7, 8, 6, whatever, but 4 colors, and even there. And also think in terms of how balanced they are. So now I have 4 oranges, 4 reds, 4 yellows, and 2 blues. Okay? So reasonably. Think in terms of if this particular graph represented some complex computation that you have, right? With the edges representing the dependencies. I can process this one color at a time and not have to worry about any conflicts or deadlocks. Does everybody see that? So, especially when you get to really ugly computations which are hard to parallelize, it's worthwhile to color the dependency graph so that you can stage it. So now you can see that if I'm processing all the yellow, so think of a loop, your code is going to look a little bit different. It's going to look like you have a loop over colors, and when I do one color at a time, I don't have to worry about it, because I will only be doing orange. If I'm doing orange, I'm only doing read access to everybody else, and I'm only writing to orange values. So no dependencies, and you have broken your deadlock in a very nice fashion. Okay? So does everybody see the motivation of why you might want to do color? Right? And this is very common. People do this for when they're designing hardware. There's a lot of these contention issues. You have these graphs which talk about dependencies, and you want to color them up so that you can effectively separate them out. So how do we do this in parallel? Again, these problems that we are interested in might be so large to start off with that it might not be possible for us to do something like this. So can we do this in parallel? What is the problem with the algorithm as I gave it, which makes it difficult for me to do this in parallel? Think of trying to extend this. But the solution I come up with is going to be ridiculously stupid and simple, so I want you to think about it first to appreciate it.
It's dependent on the neighbor's color, right? So there's a dependency. So
Yeah, so if I start coloring two of them at the same time, the states that I would be to check if some color has been used before is state, right? So two people might try to update the color at the same time, in which case that my coloring is overall gone wrong. Yes?
You could maybe split it down the middle, however you would have shared nodes in between.
Yes, and so you could think of a sort of a divide and conquer strategy is what you're thinking of, right? Which means that I can start off, I'll give you an example because people have thought of that direction, is that you can start off, split it, and pick. So in this case, let's say that we decide to split, for example, along this edge, right? So color these four guys first, and then you can color each side independently, and you can do this. But this is very expensive, right? You're sort of partitioning. How do you choose which one to choose, and then you're again recursing on this. Like I said, very, very simple, because as you can imagine, the sequential algorithm is not really that complicated, right? What is the issue? What is the problem in terms of, what did we do? So look at the formal, remember the formal definition that I said. I said choose an ordering of my values. If I could choose an ordering, which, this is symmetry breaking, right? I don't know how to define an order in parallel. So technically think of it. If I was actually coloring this guy and this guy at the same time, the algorithm wouldn't be that bad, right? It would work because they're not really sharing. All I want to make sure is that, what is it that I want to make sure?
it's not connected.
That when you're doing this, only one of me or my neighbors gets to choose his color, right? So if I can do this, then I'm fine, okay? So before we sort of get into how we're going to do this, understand the concept of an independent set and correspondingly the maximal independent set. Who knows what an independent set is?
The union is null
Union is null
with another set.
intersection. So very close, yes. So that's what I define here, that no two vertices share a common edge. Okay. So this might be somewhat confusing. Think of this as an edge, as a graph, and the independent sets listed here are the ones in red. Okay. So reds, so that is an independent set taken from this list of vertices. So in this case, the reds, two red vertices, which I picked as a set, are independent because they do not share an edge. The same is true here. So the whites are allowed to share an edge. I'm only picking the red set out. Okay? So this is an independent set. This is actually, in this case, these are all the independent sets that you can figure out. This is an independent set. This is an independent set, and so on. Does everybody understand what an independent set here is? Just, it's a subset of your graph. So in the graph context, it will be a subset such that no two elements belonging to this set share an edge. And you can sort of kind of see how this might be related to parallel. Not completely, but close enough. More importantly, I want you to tell you to understand the notion of a maximal independent set. The maximal independent set says that a maximal independent set is an independent set such that no other independent set can claim it as it's basically as a subset. So it's the maximum set that you can define. So which of these are actually maximum independent sets?
Second last.
Think about it and let me know. So is this a maximum independent set?
Yes.
Right? Why? If I add any one of the white guys, I lose my independence. Is that clear? And this has 4 out of 8, so this looks good. This one?
Yes.
This one?
No,
Why?
because you can add that
Oh,
white.
Which one?
I can't add anything to it.
This one? These two share an edge.
Lower right.
Lower.
No, same thing.
No. Oh.
So which of these are maximum independent sets?
It would all be
Two in the middle.
Which one? These? No.
No.
They're all in maximum independent sets.
So you would say-
Understand, I'm showing you this example because I want you to understand. It's not that just because you had 4 vertices that it became a maximum independent set, right? Is this clear? Now, I can obviously say that I can choose any random 2 guys who don't share an edge, and that will also be an independent set by definition, right? But we are particularly interested in maximum independent sets. And maximum independent sets that you can't add any additional node without violating this condition. Does everybody see this? Does everybody understand this? This is, like I said, I'm not treating this as a theory class, but it's a very simple concept that you should all understand because this is how we go about doing this. Is this clear? Now that I've brought up this property, what does this tell you? How does this help us? Does this help us with coloring in parallel?
Yes.
Why?
Because there is no dependency between the other set.
If I could detect an independent set, or better still a maximum independent set, then any member of this set can be colored independent of each other. Yeah? Right? There is no dependency. Which is why I don't want to be able to add one of these guys which violates my condition. Right? So I can color these 2 because they're going to have read access to this, but they're never going to write to the common thing. There's no common edge. Okay? So you can, again, this ends up being sometimes the purpose of coloring is to actually detect maximum independent sets, but in this particular case, the first algorithm that we're going to look at is sort of the first of a class of randomized algorithms looking at graph coloring, which uses the property. So the first step is to detect or to compute a maximum independent set, and then all members of the set are independently colored in parallel. Okay? If at this point, I told you this is not going to be about Spark today, but if you wanted to think of it, if I could group together some RDE that I had in terms of their colors or in terms of extracting a maximum independent set, then a simple map operation would allow me to color them in parallel with the knowledge that they would never violate each other's color properties, right? So it would boil down to a simple map operation, which would not be possible in the general case if you were not selecting an independent set to operate upon. Okay?
Question.
Yes?
Are you saying all of the red could become the same color? Is that what you're
No,
saying?
no.
Or just
No.
they're independent?
I can color them independently. So what it means is that, let's look at the first case. So again, please understand this. This is not a very difficult concept, but if you don't understand this, everything else is going to look somewhat tricky. So let's consider these 2. If I were to color this one at the top left, this one, right? His color, what is he going to do? He's going to look at his neighbor's colors, which means he's going to look at this one's color, this one's color, this one's color, and he's going to color himself. Correspondingly, this one is going to look at this, he's going to look at this, and this, and decide his color. He is not dependent on what the other guy's color is, or might change during the process. So there is no violation whatsoever. Okay? So what we're going to do, the loose algorithm is going to look at your graph, identify a maximum independent set. Okay? Identify this set, then color all of these in parallel. Okay? And then continue on to anybody who's left, who's not been assigned a color. Is this clear? No? Okay.
So because as you mentioned, so the red points, I needed to look at the 3 neighbors.
Yes.
But I needed to have the color for the 3 neighbors first, right?
If they're not colored, I can choose any color I want. I don't
okay.
care. I'm
Okay.
doing it again in an iterative
okay.
fashion. I'm just extracting the parallelism. It's not very different from the greedy algorithm. This is just a parallel version of the greedy algorithm, right? So all I'm saying is that if you're not colored, I get to choose whatever color I want, right?
So those are gonna be like every time because nothing will be colored, then you're just gonna pick.
Yeah, the first guy gets to pick red, right? I'm red. Whatever.
So they can all be the same color. Then going back to what he was saying.
It could be. So the first time, only the first time you're guaranteed that, right? But let's say you're doing this repeatedly, right? I'm not going. I can choose one maximum independent set. That doesn't mean all the nodes.
Oh, because you.
Once I color it, I'm going to pick another independent set from not containing this, right? So think of like having a big ball, a bag of white balls, right? I pick an independent set, I color them independently, maybe they all become red, which is typically what would happen. The next time I pick the set, some of these are going to share edges with the red ones, which means that they can't be red. If you don't, then well, by definition, you're not going to share any edges, so there's going to be no more reds left. You realize that? Does it make sense? If I could have colored, if I had another red ball left, it would have gone in that by definition of the maximum independent set.
Oh, that makes sense because. Alright.
Right?
Yeah.
If I could color anybody else red, I would have already picked him out in the first.
So you have to make sure you do the maximum independent set.
That's all. I'm going to present two algorithms, one which works with maximum independent sets and another which only works with independent sets, which means that it will reuse colors.
Okay.
Yes?
So when you do it iteratively, you basically throw out in the whatever you've picked up in the first iteration.
I mean, they're done. You're done with them. They're not throwaway, but you don't need to process them again.
Right, but then in the next iteration, do you still account for adjacencies?
Yes, yes. You're not processing those, so it's visiting each node once.
Okay.
But the adjacencies are still measured and their existing colors are always measured.
Yeah, but in that case, you lose parallelism, right? Because now you're down to.
No, well, let's look at it. Hold on to the thought for a minute. Nobody has actually, so you raised that question, but you didn't raise the first question, which is actually the main part. How do I actually compute the maximum independent set in parallel? Right, so so that's the first step. You're jumping ahead, right? So let's look at the independent set. And let's sort of, at least for now, think in terms of having shared memory, right? So read accesses are free, let's assume. Or you can replicate that information. And that's why, so that would answer your question, right? So I'm not bothered about that. There are ways to deal with it, maybe an extra round, but at least there's no lock, and I know how many steps it's going to take. So now comes the important part, how do we actually do this? So this is where I am not sure what the next slide is. Let me see this. So I think this is just the core algorithm, so any independent set can be colored in parallel. So what you do is that you extract an independent set from our node of vertices, and while there are some nodes left basically, which haven't been colored, do in parallel, you choose an independent set, right, from whatever nodes that are still left. I color all the vertices in I, right, in this independent set because they can be done. Then you update, you basically loop through with whichever vertices are left which were not picked in this independent set. Okay? Does it make sense? This is just the formal representation of what I said. There is a couple of strategies to think of here. This is all related to your question in terms of what color does anyone pick. And here you have an option which is to use the optimal coloring. This is a formal definition. You don't need to think too much about why it's called optimal. It just means that pick the smallest color available, which in our case would be red. So if red is available, I'll choose red. If red is not available, I'll choose orange or yellow, whatever order I specify. Now you can start thinking as colors, as labels, say 0, 1, 2, 3. So that's where the order is defined. So the optimal coloring would be that each process tries to choose the smallest available color or label that can. There's also this notion of balanced coloring. And I sort of loosely mentioned in our greedy example about this, that if I want to use colors to implement a sort of a parallel algorithm, then I would like them to be somewhat balanced. So that each stage or each color has an equal amount of work, so that you're not completely skewed. This is like in our quicksort example, I want them to be equally divided as much as possible. We're not going, well, we'll cover this a little bit, but this is just a strategy of how you pick the colors, right? In the first case, if the smallest number available, if not, I keep track of how many times a color has been used, and I pick the one which has been least used, okay? Again, a greedy strategy towards achieving our goal. I said the key part is in picking the maximum independent set. Yeah, this is messy enough, so you can, I want you to think about this. How would you do this? I'm not sure, this probably doesn't help you much, so let's see. Actually, this kind of does, what it does is that this doesn't fully reveal it. So let's start with this. You start off with a null independent set. So there are no edges, no vertices added to my independent set. And I create whatever is my current list. So while my list of vertices which have not been picked has some nodes left, I'm going to choose one independent set from V, right? Just one, anything. This could just be, we'll go into how this is done again. But for now, think of just picking any one random vertex, right? If I pick one vertex from my set, then that is independent, correct? I append it to this list that I already had. I create a new list, which is X, which is the vertex that I just picked, and anybody who's in the neighborhood of the vertex that I picked, because they will violate my independence criteria. I update my V to remove these guys, and I continue. Okay? So, if this is not completely clear, let's sort of look in terms of extending this. There's going to be an example again, but just so that you understand. So if I picked this particular one as my, actually maybe not this one. Let's pick this guy, right? So I picked this particular thing as, so this would be I prime in our notation. I was my list of maximum independent set that I'm computing. So I put I is equal to this one, right? So anything which is colored in brown is my part of my independent set. Then I say that from my total list of vertices, let me remove I and anybody who's in the neighborhood of I, which means that this, and this are removed from V as well. Is that clear? Now what is left in V? This, and this. So let me randomly pick one. Which one do you want me to pick? Okay, let's pick this guy, right? So if I pick him, these two are independent. Now let me go through and see anybody in the neighborhood of that? No. So these guys are still left. Let me pick one more. Which one do you want me to pick?
Far left.
Okay, let's pick this one, okay? If I pick this, then the neighborhood of this guy, this would have been I prime at this iteration, and I would be all three of them together. These are part of X now, right? And I'm done. Yes?
But I prime is a set, right? It's not one vertex.
It's, we're coming to it. I'm just explaining how it works. We would like to do better than this. This is one version.
No, but if it is a set, then you might eliminate the whole graph in one shot if everybody is in the neighborhood of that set.
You could, yes, and that's fine. I'm just saying that I still haven't told you how to pick an independent set or an independent set with more than one. Everybody knows how to pick an independent set with one vertex, right? Is that clear? I'm just explaining you how. So I'm going in stages. The first was how you color if you had a maximum independent set. Now I'm saying that how do you pick a maximum independent set. And for now I haven't told, all I've told you is the only way we know how to pick an independent set right now is to pick one guy. Is that reasonable? We'll see if we can do better. And yes, you're right. That is a problem, right? Because there is again a bottleneck there. If I can only pick one vertex as part of an independent set at a time, because I'm doing it. But I just want to sort of illustrate this idea first, that if I could pick an independent set, even if it is as trivial as just picking one at a time, then I'm recovering a maximum independent set. Is this a maximum independent set or not?
Yes.
Right? Because by definition we have just done this, right? So is this clear? So now comes the final part. Sorry, I keep rebuilding the suspense for this. How do you do now, since you asked the question, maybe you want to try to answer. How would we do this in parallel? Let's say we're given a graph. Let's say it's all of us being in a graph if you are in the same edge or if you're close enough. How can we pick an independent set? It doesn't have to be a maximum independent set, so we made it easier, right? The reason I've gone from coloring to maximum independent set to independent set is that an independent set is a very loose definition, in a sense that I could have just picked one, right? So if it's me and you, we are an independent set because we are far enough, right? We don't share an edge. I won't want to pick these two guys, but picking him and him is fine, right? Does it make sense? So I just want an independent set because this algorithm or this extra loop that I have will guarantee that I can recover a maximum independent set starting from an independent set. Does it make sense? So how do we pick an independent set? In parallel, which means that the information has to be very, very local. Any guesses?
If we start off like picking two different sets which are not connected even with one.
How? Think in parallel. So think in terms of the complexity of what you want to do.
So maybe if we have the information about twice the path, like double path length.
Yeah, but you're complicating things there, right? What do you want to do then? Okay, let's say that you have this information.
So if I have that information,
Then, okay, let me present this a different way. Can I do something? Let's say that you are my vertices of the graph, and I want to somehow figure out, I want to do something so that if I say independent set, each of you can independently decide whether you are part of a set or not, which means you will stand up, right? Then it's perfectly parallelizable, right? If each of you independently know whether you're part of an independent set at this iteration, then we are in good shape, correct? Which means that independently, you can, again, this is not independent at a level wherein you are completely oblivious of your neighbor because the structure of the graph is important here. But you, with whatever limited knowledge of the graph you have, your adjacency list, can you figure out who should be the one who will volunteer to be part of I prime?
so
Yes.
I have one idea.
Yeah.
If we have an adjacency matrix, so our a square plus a will give us the list of nodes that are connected through two or one path, and for all the nodes where we have a zero value, they are essentially independent.
They are not reachable by two.
They're not
But
reachable by
again, think in terms of parallelism. You want me to figure out who else is zero out here. How do I know if I'm part of that, right? Does it make sense? You can analyze it in its entirety and use that to figure out sets, but it won't extract it.
Zeros.
What are zeros in the adjacency matrix? This tells you that you're not connected to somebody else, which means that if he stands up, you can say that I will stand up. But independent of that, can you? What if you look at something and you both stand up? Right? You don't know that the other guy is going to stand up, do you? So if both of you say that I have some edges and with others I don't have edges, how do you now make sure that this deadlock doesn't happen? You're symmetric. You can't do it on the basis of that I have three edges. Maybe he can do it in the sense that there's nobody else sitting in this row, and if I limit it to this row, then he can stand up. But what about these guys? Who should stand up? There are three of them out here. How do they independently know whether he should stand up or whether these two should stand up? It's a very simplified case, by the way, right? Both of those would be independent sets, right? He can either stand up or these two can. How do you distinguish?
Oh, I was just thinking this would be really naive, but like, what if you just that same algorithm, but just on starting at every node and then like compare?
It's too expensive. Yes, you're doing one by one, but what about conflicts in this case? Because the way I would produce the independent set, and I would tend towards producing the maximum independent set, would be different depending on where I started off from. Okay, so I'll give you the solution. It's very, very simple, and the goal, the way I was, if you remember, you forgot the title of the lecture. This is a randomized algorithm. So all we do is very simple. I give all of you a random number. Okay, and I say that look at your neighbors. If you have a number which is greater than your neighbors, stand up. We are done. That's all. Does it make sense? So we've generated a random number and we have broken the deadlock. Remember, I don't need a maximum independent set, I just need an independent set. Which means if I take back this example, you three get a number, you look at these two, and everybody has numbers, right? So If you are greater than these two, you can stand up, and you know that they won't be able to stand up because your number is greater than theirs. That's all. And that's the end of the algorithm. Like I said, at the end of this, these are going to be very, very simple algorithms to implement and understand. Does everybody understand the general idea? Yeah? So sort of let me sort of hammer that in to some extent. Okay. Assign random weight to each vertex, choose vertices that are local maxima. You could come up with any other heuristic, local minima, maxima, whatever, as long as everybody agrees to this. In general, the proof, which is, I can give you a hand-wavy proof, but it's the strict proofs are much harder to show, is effectively that you are going to require C plus 1 steps. So C is the number of colors, okay? Log V, because in general, you're going to be choosing a logarithmic, sorry, not logarithmic, you're going to have square root of n, sort of a reduction in the size of your vertex, at least for sparse graph. If it's a dense graph, the dependencies get larger, but that's effectively what you're going to be doing. And we'll sort of see this with this example, right? I just assigned some random numbers to all of these guys. Doesn't matter, whatever the order. So now what should we do? What was the step? Walk me through the algorithm. What is the first thing we do?
And we pick any vertex.
No,
Like
this
vertex
is,
with
that's not that
numbers.
one, right?
Okay, yeah.
This is, why have I handed out random numbers out here? So I need to pick an independent set first, right? So which of these are independent? Which of these are local maximas?
97, 66,
66,
82,
82, and
78,
78.
and above.
this one?
Yeah.
Okay, yeah. So, is that clear? Which means that 14 gets added to this set as well. And that now is my maximum independent set. Does it make sense? So now, in parallel, and you can imagine why this is parallelizable, because the amount of information that I need is only limited to me and my data. I don't care what's happening at the other end of the classroom, right? Okay? Are we done, or what is the next step? So I need to color these now, remember. And all of these, because these are maximum independent sets, with the same color, right? So this is my first maximum independent set, and I can color them all the same. But by definition, none of the other vertices can have the same color, because if I could color somebody else blue, then they would be part of this maximum independent set. Then this is not a maximum independent set. That's right. Okay. So in the maximum independent set, you cannot. I think where one of us at least got confused is that if you can design a coloring scheme which uses the independent set and not the maximum independent set. That's right. And there you can have variability. But Luby's algorithm, which forces you to do it, and you can imagine there are basically 3 steps, right? Compute the independent set, compute the maximum independent set, and then do the coloring, right? So it's an extra loop. So the more efficient way of doing this is actually the Jones-Plasman coloring, which is a little bit different, but not, you can actually see it should come fairly straightforward way. So you don't need to generate a new random permutation of vertices every time. So I didn't mention this because I reused the permutations, but in Luby's original case, after the coloring, he actually generates a new permutation every time. But it doesn't matter. And it uses vertex numbers to resolve conflicts. And most importantly, where it actually differs is that it does not find the maximum independent set at each step. It says that why should we bother? Because think in terms of what you're doing. When you picked the first independent set, you had the maximum number of vertices picked. And in sort of this attempt to generate a maximum independent set, I'm adding smaller and smaller number of vertices to that set. That is redundant work with very low amounts of parallelism, right? So it's like saying that when I first tossed out my random numbers, many of you stood up. In the remaining set, it's harder and harder to find vertices to add to my independent set, to make it maximum. So this is useless work. So let's not do it. Let's just pick this independent set, color it, and move on. So instead of having 2 nested loops, I just have 1 loop. Pick an independent set and color. So this is the case which is different, right? So you find an independent set. they're not assigned the same color. So each of these guys is now going to do a little bit more work. So there's increased parallelism in this approach, although it's less efficient. So in the first case, I can just assign a color. I don't need to check, right? I'm done. I pick an independent set, color it, and I'm done. So I need to check it, and then you color individually using the smallest available color, okay? So it's just a matter of who's doing work in parallel or, so not very different. You pick an independent set out here, and for all purposes, you look at the colors of the neighborhood, choose the minimum color, assign it, and move on. Remove these from this thing. So it'll be fairly clear if you look at this. So some random numbers initially assigned. So let's look at it. It's going to produce something a little bit different, not too different because it's a very small case. So you pick the independent set. Let's color this and forget it, right? Nobody else, so this is easy. Now I pick these guys. These are my independent sets. I look at them. I pick the next color, which is not assigned. So in this case, yellow, because they all share an edge with the blue ones. In the next case, again, this is again, although I'm ending up picking up the same colors, for a larger case, it's not guaranteed, okay? It's just that the way they are being picked up, they end up sharing an edge with either the blue or the yellow ones. So we get this. In the next case, again, now we get red. If you remember, 14 got assigned right up front to blue. And now you can see that in this case, it's again going to do, it gets picked up as the only remaining one which is not, and it looks at it, it can either get blue or yellow. Whatever, depending on your strategy, it can pick either. Let's say it picks blue. Okay? So this is the only difference. Fundamentally, they both use random numbers to break the tie and figure out, and you can implement either of them. Okay? So in some ways, this is more easily implementable and more efficient as well. Okay? Does everybody understand the difference between the two approaches?
I have a question.
Yes.
On the Lubies, did you generate new random numbers every round?
The formal method of the original paper by Luby mentions that he wants you to generate new random numbers every time.
Okay.
In practice, I think it's rarely done because it really doesn't change.
Yeah, I'm trying to imagine why that would make a difference.
Yeah. So it's important when you try to prove it. If you make this assumption of them coming and not having a bias on the previous time, there are reasons because if again a hand wavy argument is that if you start off with a one standard random distribution, then there is a bias, or that's also a kind of a bias, which is better than having a systematic bias, but at least the subsequent iterations are biased, but it's not as bad because most of the work is already been done. Yes.
In earlier scenario, when you showed like squares, we found maximum independent sets with different number of vertices.
Yes.
We said that it really doesn't matter, number of vertices. But if we find out optimized independent set, let's say with maximum number of vertices, then we'll get more parallelism.
You will, but that's a very hard problem. So you are looking at the other case. Like I said right at the beginning, that tunneling is an NP-hard problem. The same way, finding the maximal independent set. You understand the two maximal independent sets is also NP-hard because it's related to the coloring problem. So in a sense, maybe, I don't know if this is true, in this case maybe the blue one is the maximum independent set. But that is very hard and you don't want to do it. So we are having a trade-off between doing something fairly cheap. So this is a trivially parallelizable version where I get very good results. It's not the best, it's not guaranteed, yes. But you're because there is still a bias with whatever. So if I chose a different set of random numbers out here, the first independent set I'm going to pick up and the ones which are going to be assigned this blue color is going to be different, right? The net coloring might not be that different because that is still dependent on the structure of the graph. But the way you would go about assigning it and the structure of your program is going to depend quite a bit on what numbers got assigned.
But I think no matter how you choose, it would affect the next iteration. So if you pick 4 in the first time, maybe that would affect the next rounds of maximal independence. So you cannot guarantee that at first case if you get more parallelism, that means that you would get.
No, you won't. In general, any of these steps, it's not guaranteed. And one of the reasons why Jones Plasmon is out compared to Ruby's is because it doesn't bother to maximize the coloring part of it. It just says that I want to maximize the overall part of it. So let me just go with this independent set that I have computed, which is maximum. And in both these approaches, as you have colored more and more of the vertices, the last few iterations of your coloring are going to be very low parallelism, right? Because you don't have enough left. So, but that's okay. This is the best we can do. It's a very, very hard problem. So if you think in terms of trying to do coloring without using these kind of randomized algorithms, you'll see that they are very, very hard. I actually encourage all of you to think about trying to do this, because it appears like a simple, trivial problem. I'm just looking at my neighbors and coloring, but it ends up being something which is very, very difficult to parallelize. Whereas if you use just a simple trick like this, it becomes very, very easy both to implement. There are bounds on it which are pretty close to optimal. It's very difficult to do better than these. And it's also easy to parallelize. So it's sort of like it's a win-win in every respect. Okay?
So parallelism in this problem is that we're able to color more than one vertex at a time.
Yes. And you can imagine, you can think, so you were in the other class, so you can think again, if you want to implement this in MPI or something, each process can have a small subgraph, and except for the ones in the boundary where I'll need to exchange information about what the colors are and which ones got changed. So I would have an iteration for each of these stages where I'm updating at the boundary. Everybody else is happily doing things in parallel, right? You're done. There's not really anything much to be done beyond that. So it's actually, like I said, it's very easy to parallelize in any framework, because, like I said, your access is limited to your neighbors, and that is, you can't really do much better than that, right? Any other questions?